Welcome back to che531. In the last lecture, we talked about stability analysis of forward Euler. We talked about a generic problem of dy dx equals lambda times y, and we said usually stability analysis is discussed in this context. We proved that if we apply this differential equation using forward Euler, then we get a set of equations like this, where yi plus 1 can be connected all the way down to y0. So yi plus 1 now at the end of the day is going to be 1 plus lambda del x raised to I plus 1 times y naught. Okay. Now, we know that the solution, the exact solution, is a decaying function. We proved that this is an exponential. And so the numerical solution better be decaying as well, which means yi plus 1 should be less than y naught, right? In that case, this is decaying function. And that means 1 plus lambda del x should be less than 1. If the absolute value of lambda del x plus 1 is less than 1, then as we raise this number to higher power, then this becomes smaller and smaller. And so every y will be less than the previous y. So that's the condition for stability, right? Okay, now if you open this up, 1 plus lambda del x is less than or equal to 1, which means if lambda is real, then lambda should be between 0 and minus 2. Any number between these two, lambda del x. So the lambda del x, if it's real, it should be between 0 and minus 2. However, if lambda is imaginary, that means if lambda can go imaginary, then it should be within a circle centered at minus 1, whose radius is 1. So in the complex plane of imaginary lambda del x, real lambda del x, as long as lambda del x falls within the circle, then 1 plus lambda del x should be less than 1, and then this thing is going to be a decaying function. So now, if real lambda is bigger than 0, which means we're on this side of the imaginary axis, we're in quadrant 1 or 4, we are 100% outside of this circle, which means it's going to be unconditionally unstable. Okay, so if real lambda is bigger than 0, we are unconditionally unstable. And if we are, if we have real lambda less than 0, then there's a condition, which is, this unit circle. And within this unit circle, we're going to be stable. So we call it conditionally stable if real lambda less than 0, and unconditionally unstable if real lambda is bigger than 0. So here's an example. So actually, this is the same thing. I just redid it here to show you that lambda del x should be between minus 1 and 1 if lambda is real. So, okay, so this is actually, let me see, this is forward Euler. And for forward Euler, 1 plus lambda del x should be less than or equal to 1. Right? And so if you open this up inequality, then the lambda del x should be, I think this should be 0, not, it should be 0 and minus 2. I think there's a, yeah, I believe, 1 plus del x should be less than 1. Yes, so actually there's a 1 plus missing here, so 1 plus del x should be between minus 1 and 1. So let me correct this. This should be, okay, 1 plus lambda times dx. So this number should be between 1 minus 1. And if you simplify this, we just subtract 1 from both sides, and it's between minus 2 and 0. So del x should be actually between 2 over lambda and 0. So this is incorrect. I mean, the right result is going to be minus 2 over lambda okay, now, so we know that lambda has to be negative, so when we divide by lambda, we prove here that lambda needs to be negative. So when we divide by lambda, then the sign of the direction of the inequality changes. So this should be now minus 2 divided by lambda should be bigger than or equal to dx, and this should be smaller than, actually bigger than or equal to 0. Okay, this part of the inequality always holds. You know that delta x is bigger than 0, but delta x should also be less than minus 2 over lambda, where lambda negative. So let's say, oops, we have to add another condition here that lambda better be less than 0. So that's the condition for stability of forward Euler. Okay? And so here's the script for it. I have a stability for forward Euler. I have, let's say, x from 0 to 3 with 15 intervals. Initial condition is y equal 1 at x equals 0. And I just solved that problem, dy dx equal lambda x, using forward Euler. So this is nothing but forward Euler. And then I'm going to play with lambda to show you at what lambda we become unstable. Okay, so let's put small lambda, like lambda minus 1, okay? So when lambda is minus 1, let's see what dx is. Dx is this one, is 0.2, and we said that this delta x should be less than 2 divided by lambda, and minus 2 divided by lambda. And in fact it is, so dx is less than that. So at this condition we should be stable. So let's go ahead and run the rest of the code. And you see, yes, it is decaying function. Actually I test all of them. 15, 16, 15 points, 16 points, 50 points, all of them lead to stability condition because lambda plus del x is less than, absolute value of it is less than 1. Okay. Now let's increase lambda a little bit. Let's make it 10. And you see that for 50 points, we are okay. This is a black line, but for 16 points and 15 point discretization, we are unstable. You see, solution goes up and down and never actually decays. In fact, the solution grows in time, or grows in x. And the reason is, here, 1 plus lambda x is right at the boundary, is exactly 1. It's not less than 1. And for 15 points, 1 plus lambda x is bigger than 1. And the reason is because for 15 points, our delta x is large, such that our lambda plus delta x, so lambda times delta x plus 1 is bigger than 1. So the issue is this delta x that actually has been bigger than this delta x, and this is bigger than this delta x, and that's why 1 plus delta x in here would be bigger than this, and for this case is bigger than that. Now as soon as 1 plus lambda delta x goes above or equal to 1, we begin to see this oscillation and actually growing. So for blue we have growing, for red we don't have a growing function, but it's up and down. It's not a correct result, and you see it's oscillatory. That's because we're going above the condition or beyond the stability condition. Alright, so now let's move on to stability analysis of backward Euler. We said implicit methods are completely stable, and let's understand why. So instead of forward Euler, now we're going to look at backward Euler. So here's a discretization of backward Euler of the generic problem when f is lambda y, when f is lambda times y. Okay, so now we solve for lambda, we solve for yi plus 1, which is equal to yi divided by 1 minus lambda del x. Now we can rewrite this for I, so then yi is going to be the same relation, or is going to have the same relation with I minus 1. So we just plug in yi in there in terms of yi minus 1. And what you see here downstairs actually now becomes second power. And if you keep going like this, and relate yi plus 1 to y naught, you see that downstairs is 1 minus lambda del x raised to the I plus 1 power. Okay, now for this to be stable, the coefficient of y naught should be less than or equal to 1, which means 1 over 1 minus lambda del x should be less than or equal to 1. Okay. Now this means downstairs should be bigger than 1, which means that. And now if you think of lambda to be real, then lambda del x need to be between 0 and 2. If lambda del x is between 0 and 2, then this thing is always bigger than 1. Take it back. If lambda is outside of this range, that means it's either less than 0. If lambda del x is less than 0, this is always bigger than 1. And if lambda del x is bigger than 2, then this is always bigger than 1 again. So the stability region is outside of this circle. Anything outside of this, any lambda times del x that falls outside of the circle in the complex plane will make the solution stable. Okay. So, but we know that for the real problem, the real part of lambda in here, the real part of lambda is negative, because if the real part of lambda is positive, then the solution is an exponential, but an exponential is going to be growing. So in the exact solution, we always assume lambda is negative. That is what leads to a decaying function. If that's the case, in here we see that for the real lambda del x negative, which means in the quadrant 2 and 3, we are always stable and there's no condition on lambda del x. Okay, so if lambda is negative, or the real part of the lambda is negative, which is the case always, then there's no condition and the solution is always stable, and this thing is always bigger than 1, and as a result this always decays. That's always the case for real lambda less than 0. So we call it for real lambda less than 0, it's unconditionally stable. Now, if real lambda is bigger than 0, then it's conditionally stable, but we don't really care about this part because the exact solution always grows when real lambda bigger than 0. So, bottom line is it's unconditionally stable for real lambda less than 0. And I can show you the script for it. So here's backward Euler. You can go ahead and script it the same way. I just plug in the generic form we derived in here for the loop. And now let's run this code. And you see that no matter what 1 plus lambda del x is, bigger than 1 or less than 1, it's always stable. It never actually grows in x. So this means that it's independent of the number of discretization, or independent of del x. No matter del x is large or small, the method is always stable. And that's because it's implicit method. Okay, so we covered the stability analysis of forward Euler and backward Euler. I hope this is useful. Stay tuned for the next video on the stability analysis of RK214 and trapezoidal method.